So I want to talk about our trig functions and take our triangular definition of our trig functions and kind of expand them into our circular and maybe even our unit circular definition of our trig functions. So far, we've been working with right triangles. And for those right triangles, we have labeled our hypotenuse, always the side opposite the right angle, and the side opposite our angle, just calling opposite, and the one adjacent, we've been calling adjacent. So if it's up against the angle, if it makes the angle, it's the adjacent and the hypotenuse. If it's on the other side of the triangle, it's the opposite. So as we change our angle, the measurements of these values change. And I've got some things here that's tracking them at the opposite side, the adjacent side, and the hypotenuse. So we're measuring those. So as we change the angle, you'll notice the opposite and adjacent change. The hypotenuse doesn't change just because of the way I have this scripted. But if I change the scaling factor, that'll scale the hypotenuse as well, and everything will change, except of course the angle. So I'm going to put that adjacent length at 3, just really arbitrarily. We can put it anywhere, but I'm just going to set it at 3 right now. And if you remember, we defined our trigonometric functions based on ratios of the lengths between these opposites, adjacents, and hypotenuse values. So for example, when we did sine was the ratio between the opposite side and the hypotenuse in a right triangle. So to calculate our sine value, we just take that opposite length, that's this vertical black length here, and divide it by the hypotenuse. Right now, that's this red length. That ratio, in this case 0.55, makes our sine value. And you can see that as we adjust this angle, that sine value is going to change. Now the hypotenuse, again, is staying fixed for now. But as the angle changes, that sine value changes. And notice as we get closer to an angle there of 90 degrees or pi/2 radians, it gets larger and larger and larger. What's the most it could be? That might be interesting later. And as we get to a smaller and smaller angle, since that opposite length gets shorter and shorter and shorter, that sine value gets smaller and smaller and smaller. That might also be interesting later. But one of the things to notice, that if instead of changing that angle, we change the scale, so I'm going to put this at no particular angle, actually, about 34.45 degrees. It's about as arbitrary as an angle can get. And I instead change the scale. Notice as we change the scale, all the lengths do change size. That opposite length is increasing and decreasing. The hypotenuse gets bigger and smaller. Even up in this ratio, the 2.238 and the 4.21, those values will change. But notice what happens with that ratio. That ratio of 0.57 doesn't change. That ratio of 0.57 is dependent on the angle and only the angle. We might say it is scale invariant. It doesn't change based on the scale we're at. If we change the angle, we change the value, but even so, that new value is still scale invariant. So that's why the sine, the input for the sine, is really just that angle. That angle determines what that sine ratio is. The lengths, their only job is to give us that sine value in ratio. Their actual lengths, the scale of their actual lengths don't matter. Now, when we looked at cosine, cosine should be very similar. It is just the ratio between the adjacent side and the hypotenuse. So adjacent to hypotenuse. And again, when we change the angle, the length of the adjacent changes. Hypotenuse is fixed for right now. But even if the hypotenuse changed as that adjacent side changed, as long as that angle changes, the cosine ratio will change. And we might also look, because that, adjacent side gets longer and longer as the angle gets smaller, you might notice what happens to the cosine values. As the adjacent and hypotenuse become near the same size, what happens to this ratio? As the triangle gets larger, as the angle gets larger, that adjacent side tries to get smaller and smaller and get close to disappearing. Look what happens to the cosine value. Again, that might be interesting later. Tangent, same thing. Tangent is just the ratio between our opposite and adjacent lengths. So again, as the angle changes, those values change. But notice all of the trigonometric functions, if I instead just change the scale, all the values change except the ratios. If that angle is fixed, those ratios are fixed. And this is really the first part of what the trigonometric functions are supposed to tell us. We're going to be asking these trigonometric functions for this angle, what are the ratio of the corresponding side lengths? And that ratio is going to depend on the angle and only on the angle. And we'll be able to scale things up or down however we please. However, we are going to run into a problem. Because our definitions are stuck in arguments based on triangles, I'm going to get these functions out of the way for a second. Because our definitions are based on the opposite, adjacent, and hypotenuse lengths for this triangle, we're going to run into trouble if we start trying to look at angles larger than 90 degrees or larger than pi over 2 radians. As soon as we go over here, okay, I still have a label for hypotenuse, but that's just because of the way I scripted this. But the opposite and adjacent sides disappear, and really even the idea of a hypotenuse should disappear. The reason that disappears is because this angle of 109 degrees here, or whatever angle we end up with over here, I can scale that down. Whatever angle we end up over here, this angle of 123 degrees can't live inside a right triangle. So our right triangle definition breaks. But 123 degree angles happen. 123 degrees of oscillation happens. So we'd like to have these trig functions expanded to not just the angles that live in triangles, but I'd like them to be expanded for angles all the way around, not just angles that live here nicely in quadrant 1. And we can do that, but to do that, we need a couple of tools. Well, first, I want to adjust this a little bit so we can see some of those tools. The first thing I'm going to do is take this triangle and put it inside a circle. As soon as we do that, you can see what I was using to scale my triangle was the radius of this circle. And frankly, the reason that hypotenuse survived when it got to the other side is because this hypotenuse is really just the radius of that circle. So gosh, even with just that, we can kind of take all of this, all of these arguments based on hypotenuse, the hypotenuse of this right triangle is really just the radius of that circle. So instead of calling it hypotenuse, how about we call it radius? Now notice this angle causes this ray to intersect our circle at a particular point. That point, which I'm going to call point C, has some xy coordinates. And the xy coordinates of that point C on the circle, well, let's say at this location, we've got, well, I don't want that one. How about that one? At this location, we have an x value of 2.09, a y value of 1.05. Well, notice that's the same as our opposite and adjacent lengths. This opposite length is the y coordinate of that point on the circle. Similarly, this adjacent length of this triangle, that adjacent length is the x coordinate of that point. So instead of defining our trig functions in terms of hypotenuse, adjacents, and opposites, without losing anything, we could instead just call that opposite length the y value on a circle, the adjacent length, the x value on a circle, and expand our definition for sine, cosine, and tangent to include y, x, and r instead of opposite, adjacent, and hypotenuse. Now, it doesn't change any of our values. For example, if I grab our sine function here again, notice those x and y values stay exactly the same as our opposites and adjacents. So if we instead define sine, instead of opposite over hypotenuse, as y over r, I'm actually, I'll write that down. If we define our sine function, I don't want an x there. If we define the sine of our angle to be the y value in ratio to the radius of a point of intersection on a circle, then that is exactly the same or comparable to our opposite over hypotenuse, just in different language. Now, why is that useful? The reason that's useful is as this point goes around the circle, as it goes past 90 degrees, or pi over 2 radians, over here, this point still has x and y coordinates. It doesn't have an opposite and an adjacent side in a triangle, because, again, that 110-degree angle can't live in a triangle, but it still has x and y coordinates. No more opposites and adjacents, but it does have the x's and y's, so we can still define this function. It's still the y value divided by the r value. So it's still that y value, the 1.23, divided by the r value, which used to be the hypotenuse, so divided by our radius. So that y divided by radius, that is still our sine value. And even though it's now kind of defined by that radius, you'll notice if, again, we change this radius value, yeah, the x's and the y's and the r's are all going to change, but that ratio of 0.52, that sine value, doesn't change unless we change the angle. And when we change the angle, no change in scale is going to affect that sine value as long as the angle is fixed. So this takes our triangular definition for sine and expands it to be able to work on any angle, not just angles that can live in triangles. Now, if we take this down into quadrant 3, notice our sine value has even become negative. Well, why has it become negative? Well, it's become negative because the y value is negative. down here in quadrant 3. So since that y value is negative, that ratio of that negative value versus that radius, and the radius of our circles are always positive, so that ratio is now negative, and that's okay. Our trigonometric values can go ahead and be negative. That's impossible in right triangles because we can't have any negative lengths in triangles, but we can have negative position as we rotate. And we frankly need to, because we have to be able to make a distinction between this part of the rotation up here where it's positive and this part of the rotation down here where it's negative. We need to make that distinction, so we need those positives and negatives. Similarly, if we look at the cosine value, okay, instead of being adjacent, because the adjacent value doesn't exist anymore, because again, this couldn't live in a triangle, and frankly, the hypotenuse doesn't either, but how I scripted this, it survived. But we can still take that x over r, so we can define our cosine instead of adjacent over hypotenuse as x over r. Again, down here in this quadrant, it's negative because the x value is negative. Even in quadrant 2, the cosine's negative, again, because the x value is negative. You can probably imagine where we're going with this with tangent. Tangent was the ratio between opposites and adjacents. Well, in a triangle anyway, when we were over here, we had opposites and adjacents because the angle could survive in a triangle. But once we're over here, the triangle doesn't exist, but our x, y, r definitions still hold. Instead of opposites, we have y values. Instead of adjacents, we have x values. So that tangent is that ratio between y's and x's. Well, again, we're redefining our tangent as y's over x's. And again, you notice it's negative here in quadrant 2 because those x values are negatives. Notice in quadrant 3 down here, the tangent is positive because both the x and y are negative, so their ratio is positive. If I go into quadrant 4, just because of how I scripted this, our opposite and adjacents are going to try to fly back at us. But I've still defined these based on our x, y's, and r's, so our trig functions are still going to behave the way they're supposed to. Our sine is negative because our y values are negative. Our cosine is positive because our x values are positive, and our radius is always positive. Tangent is negative because the y's are negative, while the x's are positive. Now, you do see, I say this angle can't live in a triangle, but there is a little triangle here. Even if we go to these other quadrants, you might say, okay, this 116.96 degree angle, this angle can't live in a triangle, but I still kind of see a right triangle here. I mean, you definitely see that right triangle. I think I even have some things to highlight it. No, maybe I don't. That's okay. But we still have a nice little right triangle there. And this y value still is kind of that opposite side of that triangle. The x value is kind of the adjacent side of that triangle. It's just the angle that we're talking about here, the argument in our function, isn't an internal angle of the triangle. But it still does have a little angle here, and frankly, there's a name for that little angle here that you're trying to make a triangle. It's called the reference angle. Make sure you read in your text about what that reference angle refers to. But you can take your idea of opposites, adjacents, and hypoteni and push them into these circular definitions as long as you're kind of looking at that reference angle. So all of the stuff you've been learning about thinking in terms of opposites and adjacents will still carry through into an expanded definition. Now, this is referred to as our circular definition of the trigonometric functions, but we can actually go a little further and see something kind of interesting. For that, I want to kind of zoom into this thing quite a bit, and I want to use a very specific radius. I want to use a radius value of 1. Now, we mentioned this a little bit before. When we have that radius value of 1, we refer to this circle as the unit circle. It is the unit circle because it is the circle with a radius of 1 unit. And when you have a unit circle, a couple of interesting things happen. First off, if you will allow me to switch this over to radian measure as opposed to degree measure, I know you will. If we look at this radian measure, remember our definition of radian measure. Remember 1 radian, put this at 1 radian, was the amount of angle it took for that radius to be the same as that arc length. So this radius is 1 because it's our unit circle, and that arc length is 1 when we have a 1 radian angle. And you may remember if we made this, say, bigger or smaller, that arc length, that ratio between the arc length and the radius is still a radian measure, but because the radius is 1, notice that arc length, 0.48, is the same as that radian measure. And that's going to be true all the way around. An angle with a radian measure of 2.06 creates an arc length of 2.06 on a unit circle. Now, if we made it larger, okay, the arc length and the angle don't match anymore. But if we took the arc length and divided by our radius, that 2.88 divided by 1.4 would be our radian measure. But the handy thing, again, about that unit circle, that circle of radius 1, is that the arc length is equal to the radian measure of the angle, because the radius is 1. Okay, so that's neat. Might not be the most surprising thing in the world, but that's neat. But also notice something else. Because this radius is equal to 1, look what happens in both our sine and cosine functions. That denominator becomes 1 because that denominator was our hypotenuse for our triangles or our radius in our circles. So instead of the sine being the y value divided by some radius, it's just the y value because the radius is 1. So we will often directly associate the sine of an angle in radians or degrees. We will relate the sine of an angle to the y value of a point, and the cosine of an angle as the x value of a point, as long as they are on our unit circle. If they're not on our unit circle, okay, divide by the radius of your circle. But you'll also often see these definitions as just being the y value and the x value when r is equal to 1. Sorry, I can't write with this hand very well. It doesn't change our tangent definition because the tangent doesn't care what the radius is, really. But you'll often look at values on the unit circle and deal with your angles as if they were in a unit circle because it makes for such a handy definition. So as we go around, even to our other quadrants, we see the x and y value of this position. The y values are our sines. The x values are our cosines. We still have to take the ratio for tangent, but those radius values of 1 make it really handy. It also makes it fairly easy for us to make some of the arguments that I want to leave you with. I'll have another video shortly, but just to kind of let you chew on this for a while. If we look at the possible values for sine and cosine, if of the sine on our unit circle is the y values, as this angle goes around, you'll notice the maximum y value it can ever reach is that positive 1. The circle doesn't go above that. The lowest possible y value you have, y value is 0 there, but that negative 1 y value, that's your lowest value for sine. And then it will go back up to a y value of 0. That's our oscillation. Our values for sine will go from, well, when x is equal to, when the angle is equal to 0, sine wants to throw out a 0, but then it will go to positive 1, down back through 0 to negative 1, to 0 to positive 1, and so on and so on. I know this is a little jumpy, it's not meant to be animated. Similarly, our cosine values, when the angle is equal to 0, that cosine value is the x value, so equal to 1. And then x value of 0, and then x value of negative 1. So similarly, that cosine value is caught between negative 1 and positive 1. It's never going to throw out values outside of the range from 1 to negative 1, just like sine. Now, tangent, on the other hand, as we saw before, tangent might be close to 0 or equal to 0 down here, but as we get close to that pi over 2, this value starts to get bigger and bigger and a lot bigger. Now, this is saying 1 divided by 0 is this large number. That's because this program is kind of just saying, I give up. But where this x value is equal to 0, that can't actually exist. So we're going to get an undefined point here for tangent, and we'll talk about that. That'll be fun. So, this thing is trying to just go blah, 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 blah. But this is going to become undefined when it divides by 0 there. So we got to be careful about that. So if you keep in mind this unit circle definition, when we start getting into graphing and look at how the trig functions behave, their limits will hopefully start to seem fairly natural if you can picture this rotation. Okay, I'm going to let you kind of think about that and let me know if you have any questions or there's anything you need. And I will talk to you later.